Okay, the first question from the sheet that you had in the lab session is from Chapter 15, number 90. Now, I've just done this out and the record wasn't on, so I'm not doing it over again. And what I'll do is just show you and then uncover as we go along. In this question, we're told that the Kc value is 152, the temperature is 500 Kelvin, and the volume of this gas phase reaction is 10 liters. That's the size of the flask, 10.0 liters. The reaction that's actually going on in the gas phase in this 10-liter flask is the equilibrium between nitrogen gas and hydrogen gas to form its product ammonia, and that's the balanced equation. The 2 bits of information that we are given, actually 3 bits of information, is the number of moles of N2 present at equilibrium, and that number is 0.424, but it's in 10 liters, and so we just made it a molarity right away. Okay, the same goes for the hydrogen gas. It was 1.272 moles in 10 liters, so that's 0.1272. And the ammonia was 1.152 moles in 10 liters, and that's where the 0.1152 molar comes from. After it reaches equilibrium, they suddenly cool it so that the ammonia liquefies, the ammonia gas, and it's removed. And so what happens then is that I have now a set of initial conditions, and they look just like the previous equilibrium one. I'm going to slide this up. Okay. They look just like the previous equilibrium ones, except now these numbers are initial, and I have an initial of 0. So I know that my change is going to be in the direction of products. So that's minus x. It's minus 3x because in the balanced equation it was 3H2 gas. And this will be a plus 2x because there's a 2 in front of the NH3. So that's my change, and now my new equilibrium condition will have concentrations of 0.0424 minus x, 0.1272 minus 3x, and then 2x. And I get this expression here. I get this expression here for my Kc. It's equal to 152. That was given. The ammonia gas concentration squared over N2 times the concentration of H2 cubed. And I fill in what I know. Now here's where it gets a little bit funny. We could do this out the very long way, and it would be, well, very long. Or we just happen to realize here, just happen to recognize that 3 times 0.0424 is equal to 0.1272. And so, in fact, if I multiply this by 3, I get this expression here. So what I did was to factor out a 3 from what's in brackets here, keeping in mind that it was cubed, all cubed. So 152 is actually equal to 2x all squared over 0.0424 minus x, and then what I've done with the 0.1272 minus 3x all cubed is to call it 3 times 0.0424 minus x all cubed. And that allows me in the next step to take out that 3 cubed. So just have a look at that. I still have my 2x all squared on top, 3 cubed on the bottom times 0.0424 minus x, now raised to the 4. So make sure you see the transition from the second last line there to this last line. Now what you want to do is cube this 3 so it's equal to 27. Bring it up here, and you get that 4104 is equal to 2x all squared. Let's slide this whole thing up so you can see better. It seems to go out of focus when it's too low. Now I have 4104 is equal to the 2x all squared, and then this thing to the raised to the power of 4. So if I take the square root of both sides, this is really going to simplify. So take the square root of both sides and solve for x using your quadratic formula. I'm going to skip over that part. And you will, I'll tell you what the two roots are though. You will get 0.0977 as the first root, and that's too large because it's larger than what you had to begin with in the 0.04. And the second root is 0.0184, so that will accept as the value for x. The question is asking what's the equilibrium concentration of ammonia at equilibrium, and we said this was equal to 2x, so the final answer is 0.368 molar.